Hello and welcome to the podcast According to Sci-Faith, where we discuss topics revolving around the compatibility of science and faith. I'm Joshua Göcking and you're listening to According to Sci-Faith. Episode 46, P versus NP, the $1 million problem. In the last episode, we were talking about mathematical proofs, and I also mentioned that not every proof has been taken, so there are still open issues. There are statements where we are still looking for a proof, or statements where we are not sure if it's true or if it's not true, but where there's still a proof needed to really make this clear, make this apparent. And today I want to talk about such a problem that is really still an open issue, where there is not yet a solution, there is not yet a proof that has been given out. And this is also one of the millennium problems of the Clay Mathematics Institute, which basically at the beginning of the millennium, they gave out some things that are not solved yet. I think it's about 7 issues or something that have not been solved yet. And among those is the problem we will talk about today. And they did not just mention these problems, but they also have a prize money award money that you get if you solve them. So if you solve one of these problems, they will pay you out $1 million basically. And there is only one of these issues that they stated has been solved by now, and that's the Poincaré assumption basically, and this has been solved. I will not dive in deeper into what this exactly is, but the funny story behind it is so a Russian mathematician has solved this issue, and they tried to give him the prize money, but he rejected it, and also he received, or he was. They wanted him to receive the Fields Medal for his work on this. The Fields Medal is basically kind of like the Nobel Prize for mathematicians, and is also connected with a lot of prize money. And they also wanted him to award him this Fields Medal, but he rejected that too. So interesting fella. But the other problems are not yet solved, and for the problem we will talk about today, which is P versus NP, this is also not solved today, but there's currently also a lot of work going into the trying to solve this problem. And this is an issue out of computer science, and there it is the case that there are certain problems that a computer can solve. But there are many problems a computer can solve, but the question always is, how fast will he be able to solve it? So let's say you want to, for example, sort a list alphabetically, and then you can ask, can give an algorithm to your computer, and he can solve it. But depending on how good your algorithm is, this can take rather long, because there are different kinds of ways to do it. And if the way to do it is really inefficient, then it might take a lot longer than if you have a really efficient and sophisticated algorithm with which it might work a lot faster. Therefore, you need not only to distinguish between problems that you can solve with the computer, because there might be problems with which you can generally solve with a computer, but if there are a huge number, if the problem is bigger and you need to solve for example, sort a huge list, and the computer can only solve this in a certain time, and then if the list is too long, then basically the computer will take, for example, weeks to do that. Is not a case for any computer for a sorting algorithm, but just as an example, if this is the case, then it is useless to you that a computer is able to solve it if he takes too much time to do so. So therefore, it's not only important to know whether a computer can solve a certain problem, but it's also important to know in how much time he will need, depending on how many entries or how much you give in to this computer. And then there is this distinction between algorithms that can solve a problem in polynomial time. So if you know from mathematics, a polynomial is basically something which goes with some potency. With, for example, x squared would be a polynomial, a simple straight line. X would also be a polynomial, and there are different degrees. You can go to the third degree, x to the third power, and so on. And these are basically polynomials, and they, if they're, what it means if an algorithm can solve a problem in polynomial time, this basically means that if you have x number of steps or x number of entries, then the algorithm can solve them in this polynomial times the length of your list, for example, steps or calculation steps, because that's basically what in a computer what makes the time, what the steps of computation. So how many computation steps does the PC or the computer need? This tells you how fast it will be, because that's what a computer does. He does one calculation step after another, and if he needs too many steps, then even the fastest computer will be slowed down by the many steps that he needs to take. So this is the first part. This is basically P, what the P of P versus NP. This is the set of problems that can be solved in polynomial time. For example, it could also be that there are problems that are only to be solved in exponential time. Then this would be much harder, because if then the set gets really big, then of course this will take really long, because exponential means exponential. So it's really that it's scaling really fast. But for a polynomial, the scaling is not so fast, and therefore if something is solvable in polynomial time, even if it is a polynomial maybe to the degree of 10 or something, it's still manageable for a computer in a reasonably amount of time to solve it. That's the idea behind it. So that's what P is, and now we need to ask what NP is. And NP is the number of problems where you can, if you give a solution, and you want to verify the solution. So in this, you have an algorithm that can verify if to a certain problem, the solution that you propose is really a true solution. Okay, time for a short break. This time I will not read an excerpt from my science fiction novel Alien Thoughts, because there are great news. For if you are an English listener or only English-speaking listener, then this might not be that big of a news for you. But I wrote a new book. It's a crime novel. It's also about topics like software development, open source, and so on. However, it's right now only in German, and it's also part of some competition where I could hand it into some publisher in Germany, and if it gets really well, then I might be able to receive an award or something like that if I'm really lucky. But still, it's currently published only there, and therefore also the rights are of course only there. So until then, I cannot publish it otherwise, also not in English, I think at least. But just to keep you informed about what's going on, and this is the book is called The Odysseus List. Also, this is a pun in some sense, so I'm not sure when I translate it how I will resolve that. But if you are a German speaker, or if you can understand the German language, then I really encourage you to get it. It's in Thalia. You can get it there. You can order it as a print book. There's no ebook yet. So if you are fluent in German, then I encourage you to read it and to order it, and to also write a review, because this is always helpful to me, and of course also for the competition itself. So if you are interested in this, then check it out. It's called Die Odysseus Liste. and as soon as there is a development in getting this book out in English, you on this podcast will be the first to get to know about this. For example, so there is this mathematical rule that every number can be factored into prime numbers. So you can have, for example, if you have the number 6, you can factor it into prime numbers, into the number 2 and 3, which are both prime numbers. And if you multiply them, you get the number 6. And this you can do with any number. Maybe you will have more than 2 prime factors, or maybe you will just have one if it's a prime number itself, of course. Or you will have a lot of prime factors, maybe the same prime factor also several times. For example, if you would try to factor the number 8 into prime factors, you would just take 3 2's. 2 times 2 times 2 would be 8. So, and this we know is possible. So there is a unique set of prime factors for each number that there is. This is could be mathematically proven. We know that this is the truth, and it's however, there is no computer algorithm which can do this in an efficient way, which can do this in a way that it is happening in polynomial time. So we know of no algorithm which can do this. So to factor a number into their prime factors is not possible in this way. However, what is possible is that if I have the prime factors, if I know the prime factors, or if I think I know them, and I put it in the computer and I say, check if these prime factors manage to get this and that number, then of course this is just a simple calculation, then the computer can do this. And therefore NP are the problems for which this is fulfilled in polynomial time. So in there you can basically compute can verify a certain solution. This is basically what NP is. So what we see from there is that P is already part of NP, because since P is the number of problems that for which you in this polynomial time can find a solution, if you can do this, then you can surely also verify a certain solution, because you can find the solution itself, so you can also verify any solution. So P has to be part of NP. So this part of the question is already solved, because the question is whether P is equal to NP. So the question is whether it is possible for every problem where we can, if we have a solution where we can verify it in polynomial time, the question is if all these cases where this is the case, if we can find an algorithm which would solve these problems in polynomial time. So can we find, for example, an algorithm which would be able to find the prime factors of a certain number in polynomial time? Would this be able? Does the fact that we can verify a solution or verify for certain prime factors that it is indeed that these are indeed a prime factor of a certain number, does the fact that we can do this in polynomial time also mean that we can find an algorithm that will get us the prime factors of this number in polynomial time? This is basically the question, whether P is equal to NP. And as I have said, we know that P is part of NP, so we know that this one direction is already holding. So we only need to show if the other direction is true. If we given a problem in NP, if this will also be a part of P, if given that we can in polynomial time confirm a solution to a certain problem, whether this also means that we in polynomial time also can find this solution to this problem directly. this is the big open question that mathematicians and hobby mathematicians try to solve and are researching on. And up to now, they could not find a proof. And the assumption is, of course, that this is not the case. So the assumption is that P is not equal to NP. And I think if you could follow what I was telling you, if you could follow the logic of this problem and understand what this is about to some degree, you might also have this intuition that that is not true. I mean, just because I can give a certain solution to a problem, and just because I can verify it with some algorithm, that does not mean that there has it has to be a kind of equally efficient algorithm which can solve the whole problem itself. That does not necessarily need to be the case, right? So that's just intuition. It might as well be true, but right now the assumption is that it is in fact not true, that P is not equal to NP, and that's the state where it is now. But until there is no proof of one or the other, until then it's basically we cannot say what is true, which way it is. We cannot really say this for sure. So the question is, why is this important? Is this just nice reasoning? Is this just fun for people who like to do proofs, or is this just to give $1 million to people who are pretty smart, or something like that? Or is there something behind it? And actually, there is something behind it, because most of our encryption systems are based on such things. Because I was talking about the prime factor. Factors, that every number can be separated into prime factors, and this is highly used in encryption systems, because they use the prime, they know the prime factors of the number that they have, and from this they use this to encrypt in a certain way. I don't want to dive into the details, but what the fact is, if it would be possible to put this number into its prime factors in a direct way. So if you could show that this is a problem of P that is solvable in polynomial time, then you could basically hack most of our encryption systems. You could basically go around most of these security algorithms, because you could, what they are relying on is that with the current algorithms, to put these numbers in their prime factors will take a long time, since these are not just small prime numbers, these are huge prime numbers, and therefore it will take a long time, much longer than it would be reasonable. So we are talking about years or even thousands of years here, because the algorithms to solve this are just not that efficient. But if you could show that there is an algorithm which is much more efficient because it runs in polynomial time, then this would be a real problem, because our security system would then be really fragile, because as soon as somebody would find this algorithm, he could basically hack all the systems in the world, basically, as I understand it. So, and there's also these other things. There are these one-way functions, basically, what they are called. So this is if you type in your password somewhere, or if you are logged into somewhere and you type in your password, they, of course, in some sense, they need to store your password to know if you type it in, if it is correct or not. But actually, that's not really what they do. So they don't, on their servers, they don't write in your password in plain text for everyone to read, basically, because that would really be really dangerous. But what they do is they hash your password. That's what it's called. So they have this function, which is a one-way function. What that means, it cannot be turned around. So they can, from your password, they can create this hash, but from this hash, it is, at least that's the assumption, that it is not possible from this hash to create your password. So to reconstruct your password, this should not be possible. So what they do then is they have this hash of your password. This they have in their servers. They also put some other things above it to make it even more secure, but that's another story. And once you type in your password, what the server does is it immediately hashes your password, goes into the table with your password or into the database, and confirms the hash it has there with the the hash of your password. And if they agree, then he knows, okay, you seem to be the one who knows the passwords, you seem to be the right person, and then he basically lets you access. One problem with this is that in this one-way function, it is not clear that that this will always yield an unique result. So in principle, it could be that there is a different password which would yield the same hash as the hash of your password, and therefore this could get difficult, but it's really unlikely that this happens. So it might be, but probably it's not a case. But also what's not clear is if this is really a one-way function. So there is no clear proof that these functions that are used there, that they are really one-way functions and that they cannot be turned around, because if P would be equal to NP, then these one-way functions could not exist. So if one could show that P is equal to NP, then one knows that it is in principle possible to reword these functions and basically from the hash restore your password. So the fact that, or this let me say it like this, you better hope that P is not equal to NP, because if it is, that would mean that we would need to think of a whole lot of new security systems, because our current security system would all be compromised, and it would only take somebody to find the correct algorithms to hack them all, to get into all these systems. So I hope you could get some idea about what this P versus NP issue is, and if you are excited now, you can try to solve this problem yourself. As you have heard, there's a lot of money to be won if you manage to do so. So that's everything for today's episode. I hope you liked it and you enjoyed each part of it. If you want to get in touch with me or discuss a topic or want to give me some feedback, then feel free to contact me using the contact form on my website, sci-faith.de/en. And there you can go to the contact tab and contact me. And if you have any other things or episodes you want to have covered there, or topics you want to have covered, feel free to contact me there. Also, if you are not yet familiar with the format in which this podcast is produced, let me just briefly explain it to you. So there is always at the beginning of a month or of a block, there is a big block of 4 episodes in one thing. It's kind of like a preview, which I call it, where you have the next 4 episodes all in one episode together, combined. And this is for people who like to hear long format podcasts, who have a long way to work or something else, where they can listen to a long episode and can then have a preview of the next 4 episodes all at once, and are completely up to date from the beginning of the block. For those who like their episodes shorter, who prefer it if they have a half an hour or even less of a podcast episode, for those there is every week afterwards will appear a podcast episode almost in that length, and this way I can publish every week a new podcast every episode, and everyone can have it his own way, either once a month a long chunk of content, or once a week a shorter format podcast episode. So I think that's the best way for everyone, and also for me when I'm producing it. Please also note that this is an independent podcast, which means that it is recorded, produced, and marketed by me. So I really need your support in this. So if you like this podcast, then give it a 5-star rating. And if you have the time, even write a review to it. This just helps other listeners to become aware of this podcast, and then people who might be interested in this content can become aware of it. Also, if you have friends who you think would like this content, then recommend it to them and share it with them. Also, you can support me in other ways, for example by reading my blog and subscribing to my newsletter, or even by reading my books, which you can find on Amazon. For example, there is my latest novel out now is Alien Thoughts, which is pretty entertaining from the feedback that I gotten, and so it's also in some way related to science and faith. The topic of it is also in there, but of course you can also read the book to this podcast, Sci-Faith, The Compatibility of Science and Faith, which is also available in English since last year. Thank you for that, and now I wish you a wonderful day, and I'm looking forward for you to tune in again next time.